Welcome to ICDD's InSession webinars and Justin Blanton's presentation, New Features of the 2026 Powder Diffraction File. Please remember to visit icdd.com for information on free webinars, educational events, PDF databases, and JADE software.
Okay, thank you for joining us today. This is the New Features in the 2026 Powder Diffraction File webinar in session. My name is Justin Blanton, as Monica had said, and I'm the Engineering and Design Manager at ICDD. And in this in session, I'm going to be showing you many of the new features that you'll find in the new 2026 version. Now, this version was just released only a few weeks ago. So this just came out at the beginning of September. Okay, so the first thing I'll mention is that calculated intensities are now scaled to 100%. So for historical reasons, intensities for calculated diffraction patterns originally were scaled to 1,000, and this was using integers. So there was no decimal places for these intensities. And the reason back then is because the computers could not store the intensities to floating point values. So we had to use from 0 to 1,000 to capture that dynamic range for the intensities. But now that we don't have that problem anymore, we can now easily store and display these intensities to 100% using floating point numbers. So if you had an intensity that was at, let's say, 621, now you will see that calculated intensity as 62.1%. Another new feature that you'll find are thermal ellipsoids for the 3D molecular structures. So for PDF entries that have anisotropic thermal displacement parameters, thermal ellipsoids can now be displayed in the 3D structure viewer. So these thermal ellipsoids, they're used to indicate the magnitudes and direction of the thermal vibration of atoms in crystal structures. And the size of the ellipsoid is scaled so that it occupies the space in which there is a particular probability of finding the electron density of the atom. So as I go through this presentation, you will find that many of these new features only apply to the PDF4 and PDF5 Plus databases. Some of them do apply to all the databases, and that does include the PDF2 database. But for example, in this feature, the thermal ellipsoids, this only is available in PDF4 and PDF5 Plus database software. And that's because the molecular structure and the atomic coordinates are only available in those databases. Okay, so let's do a database demonstration. So I'm going to show you the database here. And we're going to open up a PDF card that has anisotropic displacement parameters. Now, I know the PDF card ahead of time, so I'm just going to open up this selenium sulfide pattern. Okay, so here's the PDF card. Now, if you're not familiar with the PDF software and the PDF card, what you'll see at the top of the PDF card is a toolbar that contains various simulations and tools associated with that PDF entry. So I'm looking at a selenium sulfide entry, and you can see that there's 3D molecular structures available. There's a bonds angles browser. There are some electron diffraction pattern simulations available. So you have an SIeve pattern, an EBSD pattern. There's also a 2D ring pattern simulation that's available. And you can view the standard 1D diffraction pattern, which is for the X-ray diffraction data. Now, I'm going to show you at the bottom here where you have different tabs of information. There's a tab on the left side that says structure. So when I click the structure tab, we can now view the atomic coordinate information for this PDF card. So I'm just going to expand this window a little more. And if you look at the bottom, there's a table that says anisotropic displacement parameters. So because this particular PDF entry has these anisotropic displacement parameters, also referred to as ADPs, we can then simulate the thermal ellipsoids for the molecular structure. So to get to the molecular structure, at the top toolbar, click the 3D structure button here. Now this views the 3D molecular structure into a separate window. And if you look at the right-hand side, the toolbar here, there's various display options. So the new feature for this year is the option that says Show Thermal Ellipsoids. So when I click that, that has now transformed those atoms using the ADPs to the respective thermal ellipsoids. So you can see that they're now an ellipsoid shape here. And of course, I can manipulate and rotate the 3D molecular structure using the mouse. And another cool feature is I can actually increase the number of displayed unit cells. So if we want to view this by, let's say, 2 unit cells wide or even 3 unit cells wide, we can do that, and we can rotate the molecular structure, and we still have preserved the thermal ellipsoid setting here. Now, if you want to turn off the thermal ellipsoids, simply just uncheck the checkbox that says Show Thermal Ellipsoids, and that'll take you back to the standard molecular view. All right, so I'm going to go back to the presentation. Okay, so the next feature you're going to find is the ability to simulate 2D ring patterns from SIEVs. So in addition to simulating 2D ring patterns from PDF entries, 2D ring patterns can now be simulated from a user-imported SIEV. So if you're not familiar with a SIEV file, it's a file that has the extension .CIF, so that stands for crystallographic information file. And for this feature, it requires crystal structure SIEVs. And that's because to simulate a 2D ring pattern, you need to have the atomic coordinate information in order to simulate the d-spacings and then transform that to a two-dimensional ring pattern. So there's various different types of SIEV files that you may encounter. A very popular one used for X-ray diffraction work is a powder SIEV. But in this case, you do need a crystal structure SIEV. So let's go back and do another database demonstration here. Okay, so to do this, what we're going to do is we're going to close the molecular structure. We're going to close the PDF card. And now at the top, we're going to click the File menu, and then we're going to click New Ring Pattern. So this opens up a new ring pattern window. So there's nothing actually being simulated at this point. So to import the crystal structure SIEV for simulation, we're going to click the File menu at the top, and then we're going to select Simulate Pattern. Now, if I select from PDF entry, that's going to prompt me for a PDF entry in the database, and that will simply simulate the 2D ring pattern from that entry. So that's not a new feature. So what I'm going to show you is when you click File, you select Simulate Pattern, and then you select from Crystal Structure SIEV. Now I'm going to select my Crystal Structure SIEV here. So this is an LAB6 pattern. And now if you're not familiar with what it looks like, I'm actually going to quickly show you what that looks like here. So I'm going to open up this SIEV file in Notepad. And here is the SIEV file. So some of the tags that you would need to have would be these chemical name and chemical formula tags at the top. You also need to have the unit cell information. And then you need the atomic coordinates. So you need the space group structures, or I'm sorry, the space group symmetry operators here. And then you need your atomic coordinates. And then optionally, you may have the ADP values in these SIeve tags. So that's what a typical crystal structure SIeve looks like. Okay, so let's go back and let's select that crystal structure SIeve in the PDF software. And now we have easily simulated the 2D ring pattern for that crystal structure SIeve. Now, what is really cool is that once you simulate that pattern, you have access to all the typical simulation settings here on the right that you would if you were simulating a 2D ring pattern from a standard PDF entry in the PDF database. So since we were able to simulate the despacings, which are independent of the wavelength, we can actually change the wavelength to match the wavelength that we are working with in our lab. So if you want to change it to Molly, you can do that, or you can do FE. And once you've set your wavelength, then you can actually change the crystal light size. So if I lower my crystal light size to down to about 100 angstroms, you'll notice that the rings are going to dynamically get more broad. And this is because I have lowered the crystal light size for the ring pattern simulation. Now, of course, you can easily change the crystal light size and raise it back up to a higher value to get those more narrow rings. Now, sometimes you might have rings that have a low intensity, and in those cases, you may want to change the intensity scale. So right now we have it set to a traditional linear scale. You can actually drag this multiplier here to bump up the intensities. So this is bumping up the linear intensities. Now you can set a square root scale or a log scale, and that just easily shows you some of those lower intensity rings. So that's how you import a crystal structure SIeve for a 2D ring pattern simulation in the database. All right, so let's go back to the presentation here. And let's switch gears a little bit. So I showed you some of the new features that you'll find in the PDF software with regards to some of the simulations and the molecular structures. So now we're going to look more into the phase ID point of view. So in the PDF software, if you have a PDF4 or a PDF5 plus database, that's going to come with our SIeve Plus software, which is used for phase ID. Now, if you have a PDF2 database, that's going to come with our SIeve software, which also does phase ID, but it's more geared towards qualitative analysis, and it doesn't have some of the advanced quantitative analysis features that you will find in the PDF4 and PDF5 plus databases. So one of the new features that you'll find is the ability to import 2D diffraction patterns from the ESRF. So these are star.edf file extensions, and these come from the European Synchrotron Radiation Facility. So we actually have users at the ESRF who we've communicated with, and they have these 2D files that they wanted to import into SIeve Plus for analysis. So we were able to get the file format from them and then implement that into the database. So this is just one file type out of many different 2D file types that we support. We do support all the major XRD instrument vendors, and we also support some open formats as well. And you can actually import raw images. So if you look at the screenshot on the right, I'm showing an integration of a 2D XRD pattern. So this is LAB6 again. This is from the ESRF. So I would like to thank them for providing us with that data. Now, another new feature is we've simplified the sector integration with 2D diffraction patterns. So I'm going to show you how that is done in a database demonstration. All right, let's hop on over back to the database. Okay, so now we're going to open up SIeve Plus. So on the top toolbar, there's a button that says SIeve Plus here. So I'm going to click that button. And here we've opened up SIeve Plus into a new window. We don't have any diffraction patterns imported at the moment. So I'm going to show you how you can import a 2D diffraction pattern. And we're actually going to be importing a pattern from the ESRF. So this is one of the new file types that you'll find in the 2026 version. So to import a 2D diffraction pattern, on the toolbar on the top left side, we're going to click the button that says Import 2D Diffraction Pattern. And now I'm going to select this is my LAB6. It's a .edf file. And before it imports, it's actually now prompting us for an additional file. It's telling us to select a calibration file. So this is actually a new development in our software. Traditionally, when you import 2D data or 2D patterns for analysis, in the metadata of the file, that will usually contain all the data that's necessary for integrating and importing that pattern into the database. So in the metadata, you'll typically find your instrument settings, such as the wavelength and the camera to detector distance. You'll also find the image settings, such as the pixel size and the center value. But for these ESRF patterns, they've actually stored their instrument settings in a separate file. And I could see how that could be useful. So if you had multiple 2D patterns and you just wanted to store the instrument settings in a central location or a central file, I could see how that could be useful. So we're going to select that calibration file here. And that actually has an extension of .poni. And now we've imported this pattern. And let me just resize this so you can get a good view of the 2D image. So what it has done, it is actually imported the 2D image that you can see on the left-hand side. It's set the X-ray wavelength, which is 0.354 angstroms here. It set the camera to detector distance, which is 60 centimeters. It set the geometry to a flat detector. And it's actually set the image settings, so it's set the scale, so the number of pixels for the scale, but it actually did not set the centering value. So sometimes you'll find occasionally metadata may not contain the center value. Perhaps they want you to use a calibration technique in your analysis software. So in SIeve Plus, there's actually two ways that we can set the center value of this 2D image. And it's crucial to set this 2D centering value because in order to integrate this 2D pattern down to a 1D pattern, we need to know with a high degree of accuracy where the center value is. So the first thing you could do is you could click the button that says Set Center. And then it creates this red centering ring. And then using the mouse, I can drag the centering ring and I can set from a visual standpoint where I think the center of this 2D pattern is. So I just set it here using my mouse. If I use my mouse wheel, I can actually increase the radius of the centering ring. And that just kind of helps me align the centering ring more closely to one of the diffraction rings in the image, perhaps giving me a more accurate centering value. So that's one way that you can center or set the center of the 2D image. The second way is you can actually just type the center value yourself. Perhaps you've used some third-party software to calibrate the centering value for you. Perhaps the instrument scientist actually has the center value and they can just give it to you. So in that case, you can just type the center value itself. So let's say I know the center value is 4081.22. So that would be the X location in pixels. And let's say I know the center value for the Y location is 2321.29. So once I've typed in those two values, it's going to reintegrate this image, and it kind of shifted the peaks a little bit. But we essentially have gotten the same integration here. Now, I mentioned there is a new feature where integrating the pattern is just a little easier from a graphical standpoint. So by default, it does integrate over the entire image. So this includes some of this high intensity that's kind of recorded in this brightness here at the low angle. Now, if we want to exclude this region from our integration, what we can do is we can click the Integrate Sector button here, and we could use our mouse and drag the area outside of this intensity here. But what I'm going to do is I'm going to just use these sliders, and I'm going to just click the Start to Theta, and you'll see we've created this green centering ring or green integration ring. And this is showing us where that integration is going to begin. So we're going to begin the integration at 4 degrees to theta. So we're going to exclude this initial intensity. And then for the stop to theta, I'm going to use these spinners and then go down to, let's say, 34 degrees to theta. And now you can see we've created this stop integration ring here on the higher to theta. So this is just showing us where the integration starts and where the integration stops. And now we've kind of gotten a better integration of the 1D pattern you can see on the right-hand side. So I'm just going to go with this. I'm not going to spend too much time on this process for the demonstration. And now I'm going to click the Process button. And now we've actually integrated the 2D pattern down to a 1D pattern, and then we've processed the data. And when I mean process, we have removed the background and we've used a peak search algorithm to get where we think these peak positions are. So I'm just going to go with the settings I have here. Now you could spend some time and just kind of go through and make sure that it gets all the peaks, but I've got all the main peaks covered. So I'm just going to import it as is. And then before I import it into SIeve, I do want to mention that one of the powerful features of the PDF databases are our subfiles. So we have a lot of expertise that goes into classifying and categorizing all the PDF entries in the database into specific subfiles, also known as categories of information. We have consultants, we have task groups, we have experts in the respective fields, and we tap into their brain power, and we then categorize the PDF entries into these unique subfiles here. And you'll see here are a list of all these subfiles. So this is a really powerful feature that you're not going to find in any other diffraction database. So for this example, I'm just going to use the common phase subfile. So this is a pretty common material, but really using these subfiles allows me to kind of target the patterns of interest in the database. Otherwise, we would be searching over 1 million entries in the database, and that just brings up the opportunity for false positives. So I've set my subfile, and then I'm going to click the Apply Filter. And here is my LAB6 pattern that we've matched. So here are all the matches at the top. And then at the bottom, you'll see here is the 2D analysis. So the top half of this analysis here, that's actually the 2D image that we had imported. And then the bottom half is a simulated 2D pattern for the LAB6 pattern in the database that I have selected here. Now, as I had mentioned, sometimes the lower intensity rings are hard to see, so I'm going to bump up those intensities using a square root function. And now we can kind of see those intensities become more bright and visible. And if we do a log intensity, now they're even more visible. So what's really nice is that when you're in the 2D analysis view, you can change the crystal light size. So right now we have set to 500 angstroms, but if I lower this, it's going to dynamically lower the crystal light size and make these rings more broad. And then I can increase the crystal light size again. And then I can import and zoom in here and then get a better view of how well the rings of my pattern match the rings in this 2D image. And you can see there is kind of a slight shift that is going on. It seems to kind of increase as you increase the 2 theta range here. But nonetheless, we were able to easily match to the LAB6 patterns in the database. And you can always go back to your 1D view if you're more comfortable viewing the analysis in the 1D mode. Okay, so let's look at a few more features that you'll find in SIeve+. So you can now combine the search history with your common filters. So there's no need to either select a previous search history or select one of the common filters. You can actually combine those when you're doing your filter in SIeve+. We've added a new deep search option. So when this deep search option is selected, the current search will use all the permutations of the 8 strongest search peaks to the 3 strongest database peaks. Those are the database peaks that you're searching for, instead of just the strongest database peak. So essentially, we're increasing the permutations of database peaks that we're searching. And this is going to allow us to find some patterns that we may not normally be able to match if they were missing some of the strong peaks. And I'm going to show you an example of how this works. Now, to go along with the deep search option, we've also added a new x-axis range option. And you have your traditional restrict range option. That's where you restrict your range to the experimental data. But now there's a new option where you can view the full range of the x-axis. And this is going to become more clear when I show you a database demonstration of this. And you can also now hide your phase plots in the visual analysis view. So if you look at this right screenshot, we are showing phase ID of a zeolite where it's actually missing the strongest peak, but using the deep search option, we were able to essentially match to the correct phase. All right, so let's do another database demonstration. All right, so for this example, I'm going to import a 1D diffraction pattern. So to do that, we're going to click the Import 1D diffraction pattern button on the top left-hand side. And this is going to be a SIeve file that I have here. So here is my 1D diffraction pattern. Now I have some processing settings that I created beforehand to kind of accurately get where all the peaks are. Now, one thing that you may or may not notice about this particular diffraction pattern is that you have this strong peak over at, this is 23.8 degrees 2 theta. So it looks a little strange in my opinion because you have this strong peak over here, but you don't have any stronger peaks at the lower angle. So right off the bat, it looks like this diffraction pattern is either truncated or missing data. We're going to import this anyways. So we're going to import this diffraction pattern. And again, before it imports, it's asking us, do we want to apply any type of filter to our search? So for this example, I'm going to use another subfile. Now I'm going to use the subfile micro and mesoporous. So I'm going to click this. Now you'll notice for this particular subfile, there's actually a plus button next to it. So when I click that, that actually opens up a sublist of additional subfiles here, although we actually call these subclasses because these subclasses are under the parent subfile of micro and mesoporous. So I know I'm working with a micro and mesoporous material, so I could effectively just select that subfile and get my match. However, I do want to show you that we do actually have subclasses underneath some of these subfiles. And in this case, I'm actually working with a zeolite. So I'm going to select my zeolite subclass underneath the micromesoporous subfile here. And if we look at the bottom right-hand side, this is telling me that there are 6,760 PDF entries in this PDF5 Plus database that belong to the zeolite subclass. So right off the bat, I know that's how many entries I'm going to be searching for. So again, this really shows you the power of using these subfiles. Instead of searching over 1 million entries, where I'm subject to false positives, the search is going to be much slower. I'm just going to be cluttered with all these different search results. Now I can really target into the materials that I'm working with. Okay, so I have zeolite selected. I'm going to click Apply Filter. All right, it's come up with franzonite as the top 2 matches. Now, if we look down here in the graph, it is matching many of these peaks. But if we look at this strong peak at 23.8 degrees 2 theta, it is matching that peak, but the intensities are way off. So if we look at the intensity, though, we've actually matched, it's not even close to this strong intensity here. All right, so what's going on? Well, I know I'm missing data in this 2D diffraction, in this 1D diffraction pattern. And basically what had happened is when this pattern was exported, the low peak, or actually the true strong peak, was actually truncated from the data. So this is actually missing the strong peak. So what we can do is at the top on the search bar, if we click this drop down that says search method, there's a new option that says use deep search. So if we click this, that has now enabled the deep search option. So we're now searching many more strong peaks in the database. We actually are now matching to the correct phase, which is this biacolite here. And I will mention that due to popular demand, this feature will be actually its own checkbox here. So it will be a lot easier to find in the next version. But what you'll see now is that since I've enabled this deep search option, we've now matched this phase perfectly, including this peak at 30 or 23 degrees 2 theta. So we've used the deep search to match this, this phase, which we weren't able to match using the traditional phase ID algorithm. Now, I had also mentioned there's a new x-axis option. And this kind of coincides with this example. So if we right-click anywhere on the graph, we're going to get this right-click menu. If we go down to the x-axis menu here, now at the bottom of this, we have these 2 new options. We have restrict range, which is the default setting. So that is essentially restricting the 2 theta range to match the experimental data. And that is about 2 degrees to 30 degrees 2 theta. Now we have this new option here that says full range. So when I click that, that sets the 2 theta range to the full range that I'm working with. And since I've matched this biacolite, that actually starts at almost 0 degrees, not quite. But now we can see we have this strong peak at the very low angle. This is only at 1.1 degrees 2 theta. This is the strong peak that was missing from our experimental data. But now we can see it because we can see the strong peak in this biocolate that's actually in the database. So this is showing us that my experimental data was actually missing the strong peak completely because the data was truncated when it was exported. But despite all that, we were still able to match it using the deep search option. Okay, so let's go back. Actually, before I go back, I do want to just show one other new feature in SIeve Plus. And I'm going to quickly load a multi-phase example. So I have this CPD-1E pattern here. This is actually a 3-phase mineral that was taken from a round robin. So I'm just going to quickly import this. So I've re-imported a new pattern. I'm going to select these top 2 matches, zincite and corundum. Click Accept Phase. And I just want to show you that when you have these multiple phases now, and let me just zoom in to a region so you can see these peaks better. On the plots list on the right-hand side, we can now easily uncheck and hide my phase plots. So this is particularly useful if you have multiple phases, particularly if you have, let's say, maybe 5, 10, or even more phases, and you want to, let's say, change the profile function. So if I wanted to, let's say, change the profile function for the zincite, I can easily change my crystallite size. And because I was able to hide those other 2 phases, it just makes it easier to see from a visual standpoint, not having those other phases clutter. So we can re-add those easily just by adding these checkboxes here. So that's just a quick new feature of how you can easily show and hide phase plots in SIeve Plus. All right, so let's go back to the presentation. All right, so we have some new Raman features. Now, in the 2025 release of the PDF4 and PDF5 Plus database, so this is last year's release, we introduced Raman spectra to the database. So this was a brand new feature, including the Raman spectra. Now we've added some more features for these Raman entries in the database for the 2026 version. So we now have a Raman analysis graph. So this is where the user can import Raman spectra from a file and add Raman spectra from the database into a graph for visual analysis. We've also added a new Raman diffraction search, and I'll show you how that works. And we added 2 new Raman display fields, the literature reference and the database comments. So let's jump over back to the database and I'll show you what that looks like. So I'm going to close SIeve Plus here. And to get to the Raman search, if you're not familiar, that's on the top toolbar here. All the way on the right of the toolbar, it says Raman search. And one interesting thing about the Raman search is that because there's only 901 entries in the Raman database so far, we actually just show all the patterns at once. So this is a little different than the traditional PDF search. Now, I did want to show you the new Raman card or visual analysis mode. So if I click the File menu and select New Raman Spectra, this has brought up a new Raman window here. Then I'm going to click the Plots menu and Import Raman Spectra. I'm going to select an actinolite here, and we support importing CIFs and CSV files. So these are just comma-separated values. So I'm going to open up my Raman data. Now, We do allow some minimal processing to the Raman spectrum before you import it. So if there was a background, you could remove that. This Raman spectrum was actually already processed, so we don't need to do that. So I'm just going to import this as is. And then I can actually overlay a Raman spectrum from the database. So I'm going to click plots and then select add Raman spectrum. And then I'm going to select this ferroactinolite that I had actually was working with before. And now I was able to easily overlay that Raman spectrum from the database to the Raman spectrum that I had imported. So that's the Raman analysis graph. Now let's go back to the Raman search. Okay, so now we're at the Raman search. Now, one thing that we did add last year when we implemented this Raman search was the ability to import a Raman spectrum and then actually do a similarity index to all the Raman spectra in the database to get a match. So I'll show you how you can do that. So there's a toolbar on the top right here with a few buttons. Now, if you click this fingerprint button, it says calculate similarity indexes. I'm going to select that same actinolite file. I'm going to open it up, and then I'm going to import it as is since it was pre-processed. Now it is actually calculating similarity indexes, and it's going to show me which Raman spectrum actually matched the best to the one that I'd imported. Now it comes up with this first one here that it's actually a perfect match, and that's because it's matching against itself. This pattern actually is in the database now. But we can actually look at some of the patterns that match almost as well. So we have an actinolite here, and you can see how it matches, but there's a slight shift along the Raman shift x-axis. There's also another ferroactinolite here, which almost matches as well here. And there's several other actinolites. So this is showing you how you can easily import a Raman spectra and then do similarity indexes to Raman spectra in the database. Okay, so let me show you. I'm going to just reset the search here. I'm going to show you this new diffraction cross-reference search. So let's look at all the actinolite Raman spectra or Raman entries in the database. So at the mineral name search at the top here, I'm going to type in actinolite, and it brings up 6 entries. Now there's a new checkbox at the bottom here that says diffraction data cross-reference. So when I click that, now we're only looking at 4 entries. And that's because this has restricted my Raman entries to entries that have cross-links or cross-references to X-ray diffraction patterns in the database. So not only have we added Raman spectra and Raman spectra patterns to the database, we now have a two-way cross-link where you can go from Raman spectra to XRD and XRD back to Raman. So let's open up this first pattern here. So this is my ferroactinolite, and let me just expand this. And you'll notice that it says diffraction cross-references 2. So if I click this down arrow button, it's showing me the 2 patterns in the PDF database that are directly cross-referenced to this Raman entry. Now you can easily double-click those entries to bring up the X-ray diffraction PDF card here. So that's going one way from Raman to XRD. Now on the PDF card, we have this Raman spectra button, and this is showing me the Raman cross-references. So clicking this will take me back to my Raman spectra or my Raman card. So we've implemented these two-way cross-references. Now I did mention that our 2 new fields for the Raman entries. So we now have this reference field, and we have a DOI for the reference. So if you click this DOI, that's actually going to bring up a web browser and take you directly to that paper. So this is just giving me the abstract because I don't have full access. But we do have DOIs now for many of these literature references for the Raman entries. And then we also have these new database comments. So those are some of the new features that you'll find with the Raman in the PDF database. So let's go back to the presentation. And let's look at some program-wide updates. So we've decreased the program startup time using a background thread. So we're always looking for ways to speed up the program, increase performance. So we were able to decrease the program startup time. File types for exporting files are now remembered between program sessions. So if you like exporting your PDF cards as, let's say, SIFs instead of XMLs, the program is going to remember that as the default setting. We've also implemented third-party library vulnerability checks during the process or during the build process. So whenever we build the software, we are taking all the third-party libraries that we use and we're checking them against the NIST National Vulnerability Database to make sure that there are no known vulnerabilities with those third-party libraries. So this is increasing overall security with the program. And this is now being required by many government entities. I will say we did have mid-year updates during this past spring. So a mid-year update was deployed back in April that added 11,163 brand new PDF entries to the user's existing PDF5 Plus 2025 database. So if you are a PDF5 Plus user and you have the 2025 database, you may have already encountered this. If you look on the left-hand side here, the way this mid-year update works is the user is prompted to download the mid-year update when they run the PDF software. Once they've downloaded this update, the user is then prompted to run the update installation. After the update installation is complete, then the user is prompted to update the database itself. So this is where the update will add 11,000 new entries to the existing database. So this is really nice because it's an incremental update. It's a small download, and this actually will take the existing database and add these 11,000 new entries to the database. So these are brand new published entries that you're inserting into the PDF5 Plus 2025 database. So you don't have to do a complete new installation to get these. We will be deploying another mid-year update in the spring of 2026. So this mid-year update will add another 10,000 brand new entries, and this will be added to the PDF5 Plus 2026 database. And we also plan on including a software update to go along with this, where we'll add support for new file types such as Nexus diffraction patterns. We'll be displaying some additional Raman metadata, which are some instrumental fields, and also possible other new features and bug fixes. So stay tuned for the next mid-year update.
Visit ICDD.com to register for upcoming webinars and to watch previous ones.